Hello, I am Irvin Miller. I would like to show you why math is the essence of your being. Your imagination and creativity is what makes you special, neither of which artificial intelligence is capable of undertaking today. Challenging boredom is what makes your life of value to yourself and your community. Rather than allowing technology to increase your boredom, you must challenge and utilize it to your benefit. Math is a formal way of developing your thinking process. Like many others, I have developed some different interpretations, helping myself understand why many others have also successfully excelled in math, and while others languish in boredom and hold a resentment toward it. Most exciting for me was to realize that our five senses sight, hearing, taste, smell, and feel, heat, and force could be described mathematically, allowing us to be aware of how to better enjoy and appreciate life. I use this tutorial. To use this tutorial effectively, read one chapter at a time, over and over, until you have a sense of your mastery, giving you a sense of confidence and understanding. In the picture followed, you can see either a young woman or an old woman. Removing the chin, you can see the young woman. Putting the chin back in, you can see the old woman. Now, try looking at this and see if you can switch quickly back and forth between the young and the old woman. Once you can do that, you've passed your first lesson. Begin by defining the basic building blocks of math. First, we have the reference point, like the zero in numbers, black in color, and the rest in music. However, we do not think of them as nothing as the American in Europe looking for the first floor. Then we have direction indicated by the minus sign and division sign. We define a unit length for the line and a reference for rotation. This is followed by a ruler and a compass for measurement. We show the dimensions of time and color. Time is measured by change, color, etc. Color is often used to represent other dimensions, heat on weather maps and height on the contour map. Zero is always misinterpreted. From the ruler, we can see that when we add zero to a number, we get the number, the distance from the reference point. By taking that concept algebraically, we can see that zero has a sign because we can take the ruler for the negative and positive numbers and join them at zero. Two numbers are occupying the same point are equal. Since the distance from zero to zero, no matter how many times we add zero to itself, we get zero. This is the first challenge for this interpretation. The geometry and algebra are self-validating. It will take a little effort to appreciate this lesson. Right now, we have a few simple rules for our mathematics. First is that if 2 points occupy the same position, they are equal. We're showing a clock-like structure which modular, where this is addresses a modular arithmetic and the concept that minus zero and zero occupy the same place on the number line. The second theorem is a straight line is the shortest distance between 2 points. We use the right triangle to illustrate this, where we can see by going from one point in the base to the um, top on an angle, that line is shorter than the right angle formed by the other two sides. We begin by making a ruler. To add a number, we put the head of the number to the tail of the other number, and then we get the results. Here we add 3 to 2. To add a minus 5, we flip the 5 and then repeat operation as we did with the 3. To subtract a negative number, we would again put it to the head as before, and then we flip the number because the fraction changes the process. These slide rules can help you understand addition and subtraction better. To use them, put the 0 under the number to which you would like to add, go to the bottom rule, and look at the number you want to add to it, and the answer is above it. To subtract, you reverse the process. You put the number on the bottom slide rule under the number from which you want to subtract, and then go back to 0. Above that is the answer to the subtraction. This will help you understand math better. We're going to take 23 blocks and arrange them in different ways. First, we will take them in groups of 10, and after we have taken out 20, we have 3 left over. This is the number 23 in base 10. For the base 6 system, we will take out groups of 6 at a time. We will have 5 left over in this case, and 3 groups of 6. So that is the number 35 in the base 6. And now we are going to take a look at multiplication. We are going to take 5 blocks, 3 groups of them. So we have 3 groups of 5 blocks, and we show each of those 5 blocks as 3 arrows. We then add those 3 arrows together, which gives us 3 times 5, which is 15 units long. We are now going to do the same thing with negative numbers, where when we multiply by a negative number, we are going to have, we're going to have 3 negative blocks. We will add them together with a line, and we will get negative 15. Basically, all the negative number has done is flip the blocks. So it has established a rule for multiplying a number times negative numbers. Division is repeated subtraction. We show in the first column where we want to divide 35 by 7, we just count the number of 7s that are in 35. First we subtract 1, then 2, then 1, and then another one, and we have a total of 5 subtractions that we've made. Another way we could do it is if we want to divide 8 into 35, well, we could try 4 8 subtracted. That gives us 3 left over. And then we have to divide 8 into the closest number we get to 8 is 1/4 of 8, which is 2, and then subtract that, and then 1/8 of of 8 is equal to 1. Notice we're taking fractions of the divisor in order to get the ones that are closest to it. We then show a way in 3 and 4 where we do it with a traditional method, but we show it where we're doing it by decades. And so first we see 25 goes into 375 10 times, we subtract that, and then we see how many times it goes into the remainder, and it's 5 times. And then we do the same thing with 376 where we have a remainder of 1, showing again how we expand this first simple test in examples 1 and 2. The most important property in mathematics is the distributive property. First, we break these up into 3 groups. First group is 5 by 5. The second group is 5 by 3. That's 15. 25 from the first group is 40. And the last group has 10 in it, or 2 groups, and that gives us 50. And 5 times 10 is 50. So 2 plus 3 plus 4, 5 is 10. The commutative property can be derived from the associative property and from the distributive property. In addition, if we write our numbers 3 plus 5, we could write that as 3, 2, and 3. And then if we associate the 2 with the first 3, we get 5 plus 3. If we associate it with the second 3, we get 3 plus 5. So we've illustrated that 3 plus 5 is equal to 5 plus 3. In the same way with the distributive property, 5 times 1 is 5 ones, which can be written as 1 times 5. Okay, 3 times 5 is equal to 3 5s. But each of those 5s can be written as 5 times 1, plus 5 times 1, plus 5 times 1. And then we can factor out the 5 and get 5 times 1 plus 1 plus 1, which is 3. So in essence, it is shown that this commutative property can be derived from other properties, making it less of a fundamental property. Later on in math, you will find out why this is important, because addition and multiplication are not commutative under all conditions. So the slide will use for addition and subtraction, which we can also use for multiplication and division. We're now multiplying by 2, and so as we draw the lines in there, we see what 2 times each of those numbers is. 2 times 4, 2 times 3, etc. Okay, and we see those answers being put inside of the table. When we put it in this form, the multiplication table does not look particularly complicated. You'll also notice that there's a white section which we have nothing in there, and those are numbers that are the commutative products of the numbers we already know. So we only need to have to use half of that table. And now we're going to go into fractions. Fraction is a part of a whole. What we do is we break that line into 5 parts, and each equal parts, and one of those parts is called a fifth. It's that simple. Now let's see if we can use that concept in multiplication and division. If we want to multiply 1/2 times 4, we break the 4 up into 4 parts, and half of it is 2. We want to multiply 4 times 1/2 inverse, we get 4 1/2, and we see that that also comes out to 2. And then if we want to divide by 2, we do as we did in addition, and invert our number. In this case, we flip it over, and 2 times 2 is 4. We have 2 2s. So basically, using vectors, we make it easy. Now we want to multiply a fraction. 1/4 is 1 broken into 4 parts. 1/3 of 1/4, we break the 4 into 1/4 into 3 parts, and we find if we count those parts, it takes 12 of them to make the line. So 1/3 times 1/4 is 1/12. The red line is 1/12 of the whole line. When we divide, we invert. The 1/4 becomes a 4, and we have 4 1/3. And now we take a number. Okay, and in this number, we start off with 27ths, the green, the 9ths, which are the blue, and the red, which is the 1/3. And each one is 3 times bigger than the other one. We can now take this line, which has 1, 2, 3 unit lengths, 2 of the 1/3 and 2 of the 1/9. And if we take all of those and convert them, we find that we can make them in 1/9, and there are 35 of them. Now we want to actually construct a fraction. So what we do is we take that yellow line, make it into 10 parts by building it up from unit parts, and then we roll parallel lines through them so they map one to another line. And then each of those lines is 1/10. So this makes it possible to construct our numbers without having to figure out how to break things into parts. The definition of a negative number is a negative number plus its inverse is equal to 0, and for fractions, a fraction times its inverse is equal to 1. We then see we get the definition of negative numbers and the definition of fractions. And here we now have slide rules. A circular slide rule, which is similar as the one that we had before, but it takes up much less space. And the other one is a Russian slide rule that I sort of inferred from what my wife as a teacher taught me about. We are now going to learn about exponentiation and complex numbers. We'll find a rotational concept in exponentiation. Here we have a vector representing a complex number rotating around the x imaginary plane. We see a sine function, which is a projection on the imaginary axis, and the cosine function, which is projection on the real axis. Somehow we have trigonometry pops out of our exponential function. Now we will see the rotation in the reverse direction, and we will see the functions have the same shape, sine and cosine. They're just flipped in different directions. And there's the movement in the clockwise direction. And now we understand something new about complex numbers. Let us do a review of the work that we've done so far. Addition is association of numbers. 10 is made up of 3 plus 7, where we've associated the 3 and the 7. Multiplication is repeated addition. 3 times 10, we repeat 10 3 times. We get 30 for an answer. Exponentiation is repeated multiplication. So 10 to the third power is 10 times 10 times 10 is 1,000. It has another inverse besides the logarithmic inverse. It has an exponential inverse, where if we have a number to the cube power, the inverse of that would be a number to the 1/3 power. But the primary inverse is the logarithm. So I've written it with a v to show that 10 is an exponent, and if we invert that, then we basically get the logarithm of 1,000 to the base 10, which turns out to be 3. With respect to minus 1, the square root of minus 1, we introduce another dimension, which is the plus or minus I. Again, notice a direction with this new introduction to our existing dimension. A fractional power has the number of answers as its denominator. An irrational number has an infinite number of roots. It is also suggested that new dimensions are created by right-angle rotations. Let's do a little bit more summary. We have a new dimension that was introduced, rotation. We found that 0 is associated with addition, 1 is associated with multiplication, and I, the square root of minus 1, is associated with exponentiation. Subtraction is the inverse of addition, division is the inverse of multiplication, and logarithms are the inverse of exponentiation. And we basically showed what minus 1 is, and we showed how a logarithm is presented so that it will act as an inverse element. As we went on our tour of reinterpreting math, we discovered something interesting. 1/3 can be written as a repeating decimal, 0.333. 2/3 is 0.66, and 4/9 is 0.444. What happens if we multiply 2/3 times 2/3, or 0.666 times itself? Well, we show here that when we do that in steps, that we find that we get two different answers. We get another answer which starts off with 4s, has a 3 in the middle, and it continues with 5 until that's 6 at the end. So we find that there are two ways of representing an infinitely growing decimal. Since with irrational numbers, they go on forever and ever, we have to truncate those numbers. So here we show the technique for getting the range of the number, since we can't get it exactly because it takes too many calculations. Let's tie this all together with geometry and algebra. We take four triangles or rectangles that are identical and we bring them together and we form a square. This geometry can be used to prove the Pythagorean theorem, the link between geometry and algebra. A squared plus b squared equals c squared. How good is this approach? Well, these are some of the problems that my students have been looking at. Areas, negative areas, how to multiply very large digit multiplications. Here's an 18 by 18, how to do multiple multiplications, multiply a number by itself 100 times, how to prove exponential identity using infinite power series, finding the logarithm of a number and raising a number to a decimal power, finding the roots of polynomials, and the mortgage problem. Having fun in mathematics is important. Here are some of the games that the children play in order to maintain their interest. The 13th dragon, how to keep them not taking that red block. Guess your number, helps with number structure. Pascal triangle, part of the proving the infinite series. And finally we have the magic squares, 3 by 3s, 5 by 5s, and 6 by 6s. This is what attacks their interest. This is 6 years of math covered in 20 minutes. The key was using the arrow as a manipulative, which explained the properties of zero and trivialized the concepts of negative numbers and fractions. It brought complex numbers in the realm of real numbers. It was used for the rotation that we did in this video. Made things very easy. We used the eye to explain anomalies in life. Here is how math applies to string theory and the meaning of life. I've given the various organs in the body and shown how they, as receptors and transmitters, play a very important role in understanding the world about us. We took an effort to apply this approach to understanding the color wheel. Black is the center color and white lies on the outer perimeters, and gray is on that outer perimeter also. Life is about change and being recognized for our existence, making the interaction with people for us to have meaning in our lives. Children must be entertained, be recognized for their academic accomplishments, and be challenged. Most importantly, they must be encouraged to ask